In applications where exponentials show up, often the answers to questions that we want turn out to be solutions to equations with those exponential functions in them. So what we should do is figure out how to solve that sort of equation, solve equations that have exponentials in them. The general idea is that if we have an equation where the variable is trapped in an exponent, like this one, then we should first isolate the exponential part and then use a logarithm to extract the exponent. We've seen that a logarithm really just grabs the exponent off of an exponential. So if we can isolate the exponential part, then the log will just grab that exponent. And if the exponent is a variable, then that means we will have solved the equation. So let's see how this strategy works out. So first thing to do is isolate the exponential part. So that's the 5 to the x part here. So we need to add 125 to both sides. That gives us 5x equals 125. And now we can use a logarithm. But which logarithm should we use? Well, this exponential is base 5, so it probably would make sense to use the logarithm base 5. We'll see later that really we could use any base, but if you have a nice choice of base like this, you might as well take advantage of it. Okay, now on the right-hand side, log base 5 of 125, it turns out 125 is actually 5 to the third power. So log base 5 of 125, right, logarithm base 5 just grabs this exponent. So we get 3. Log base 5 of 5 to the x, well, again, the logarithm just grabs the exponent, so it grabs that x. So we get x equals 3. There is another nice way to solve this sort of equation. So it comes down to the same thing, but it's sort of a different way of thinking about it. So we're looking for an x so that 5 to the x is 125. Well, it turns out that any equation with an exponential you can turn into an equivalent statement with a logarithm. And the way to do it is the base of your exponential turns into the base of your logarithm. Okay, what used to be in the exponent goes over on the right-hand side, and what used to be on the right-hand side goes into your logarithm. Now you can see doing this little rearrangement tells us what x is going to be. It's log base 5 of 125. All we need to do is figure out, well, what is that? And as we said before, it's 3. So you see, you get the same thing either way. This rearranging of an equation from an exponential form to a logarithm form really is essentially just saying that log base 5 is the inverse function for exponentiation base 5. So that's why these two equations are equivalent. Let's look at another example. So let's solve this for b. I meant to have the variable be b in here. Okay. So this time it's not as clear maybe as for what a good choice of exponent should be. I'm sorry, for what a good choice of base should be for our logarithm. But one of our bases for the exponentials is a 3, and the other is a 9, but 9 is 3 squared, so it seems like 3 would probably be a good choice. So let's take log base 3 on both sides. So log base 3 of b plus 1, 9 to the b plus 1 equals log base 3 of b, 3 to the b, boy. Okay, now on the right-hand side, the log base 3 just grabs that exponent, so we get b. On the left, we're going to have to work on this a little bit. 9 to the b plus 1, well, remember, one of the properties of logarithms is when you have something to a power inside of your logarithm, what you can do is move that power down in front. So this left-hand side is b plus 1 times log base 3 of 9. But log base 3 of 9, right, 9 is 3 squared, so log base 3 of 9 is just 2. So we get b plus 1 times 2 equals b. And now we can solve this in the usual way. So 2b plus 2 equals b, and then I guess that's going to give us b equals minus 2. All right, so done. One last example along this line. Let's solve this equation for y. this time it looks like our exponentials are base e, so we should use the natural logarithm. So natural log over here, natural log over there. And since both of these exponentials are base e, the natural log just grabs the exponent off of exponential base e, because natural log is logarithm base e. Okay, so on the left-hand side, we get y squared minus y minus 1. And on the right-hand side, natural log of e, right? E is e to the 1, so natural log just grabs that 1. All right. Now you can see this time we got an equation that's a little more complicated, but it doesn't have any more exponentials in it, right? This is just a quadratic equation, so now we can use any other equation-solving tricks we have that we know about. So for solving a quadratic, I guess we should move everything to one side and then try to factor, or just use the quadratic formula. So when we move that 1 over here to the left, we get y squared minus y minus 2 equals 0. This one does factor. It looks like it's y minus 2 times y plus 1 equals 0, and so y is going to be 2 or minus 1. All right, so that's the basic idea with solving exponential equations, right? Choose a good base, and then use that, or isolate the exponential part, choose a good base, use that logarithm to extract the variable from the exponent. Of course, sometimes there isn't a good base. So in this example, right, we'd like to choose natural log because on the left-hand side there's a base e, so we can do natural log on both sides. But on the right-hand side, natural log of 15, right? 15 is not a nice power of e. So if we could write 15 as some power of e, this natural log would just grab that exponent. But I mean, who knows what power this would be? On the left-hand side, we're okay because the natural log just grabs the exponent off of the exponential, so we get 2x. But on the right-hand side, well, this number, it's not a nice number, but we can get a decimal approximation for it if we wanted to, just by punching it into a calculator. So even though it's not a nice number, it is just a number, and we can leave it, for now, leave it just as natural log 15, and then later, if we want a decimal approximation, we can just punch it into a calculator. So now finish solving for x, divide both sides by 2, we're going to get x equals 1/2 natural log 15. Okay, and then for some situations this might be good enough, but if we actually want a decimal approximation, we can pull out a calculator. Let's see, natural log of 15 times 1/2. So it looks like this is approximately, of course, actually it's irrational, but it's approximately 1.354, it looks like. All right. So in this case, at least, even though there wasn't a base for our logarithm that was nice for both sides of the equation, we could at least use a base that was nice for one side. Okay, let's try this one. Solve this equation for a. I meant for this to be an a. So we're kind of in the same situation where there's a base. The left-hand side makes us maybe want to use 3 for the base of our logarithm. The right-hand side maybe makes us want to use 20, but it seems like maybe we should use 3 instead because the left-hand side is more complicated. So let's use log base 3. So log base 3 of 3 to the minus a plus 2. And on the right-hand side, log base 20. Sorry, log base 3 of 20. There we go. All right, on the left-hand side, the logarithm just grabs the exponent, so we get negative a plus 2. On the right-hand side, log base 3 of 20, you know, that's a number. It's hard to tell what number. It's between 2 and 3, I guess. But because 20 is between 9 and 27. But other than that, it's hard to know. So we could leave it as it is and finish solving for a. So leave this as log base 3 of 20. And then finish solving for a. So we're going to have to subtract 2 from both sides and then multiply both sides by minus 1. So that's going to give us a equals 2 minus log base 3 of 20. But what would we do if we wanted a decimal approximation for this, right? Most scientific calculators don't have a log button for any base. You only have 2 bases available on most scientific calculators, and that's base e or base 10. But remember, we can always use the change of base formula to rewrite this logarithm using any base. So let's use natural log. So it's natural log 20 over natural log 3. And then we could punch this into a calculator to get a decimal approximation. So let's see. 2 minus natural log 20 over natural log 3. Negative 0.7268. All right, so that worked okay. But you know, if we're going to use a natural log anyway, right? From the very beginning of this example, you can tell that if we're going to use log base 3, we're going to have to switch to natural logs at some point to get a decimal approximation, if what we want is a decimal approximation. So maybe we should just use natural logs at the very beginning. One nice thing about solving exponential equations is sometimes there is a nice choice of base for your logarithm, but you can just always use natural logs or always common logs. So if there isn't a nice base for your logarithm, you can always just use natural logs. So when we do that, we get natural log of 3 to the minus a plus 2 equals natural log of 20. Okay, now natural log of 20, that's not going to be a nice number, but at least we have a natural log button on our calculators. What about the left-hand side? Well, here we have, inside our logarithm, we have something to an exponent, so we can grab this exponent and move it down in front. So we get minus a plus 2 times natural log of 3 equals natural log of 20. And now we can finish solving for a. The first thing we're going to do is divide both sides by natural log of 3. So we get minus a plus 2 equals natural log of 20 over natural log of 3. And if you look, right, here's that natural log 20 over natural log 3. So we're getting the same thing. When we finish solving, we get a equals 2 minus natural log 20 over natural log 3. So we get the same thing. It's just the exact steps along the way are a little different if you choose natural log from the very beginning. There are a couple other nice tricks that show up with solving exponential equations. Here's one that math books tend to love. I'm not sure how often this shows up in applications really, but it's sort of an interesting thing to see. 5 to the 2x plus 7 times 5 to the x plus 10. It's a little hard to know where to start here because these exponents are different and there's no way to sort of get them together because right, there's no sum rule for exponents. But what we can do is this 5 to the 2x, this is actually 5 to the x squared, right? Because if you have something to a power to another power, those exponents multiply. So 5 to the x all squared, that's 5 to the 2x, which is what we started with. So when we write it this way, 5 to the x squared times plus 7 times 5 to the x plus 10 equals 0. This looks quadratic, right? It's as if 5 to the x is a variable, and so we can solve for that variable. In fact, if it helps you see how this works, you could even do a substitution. Let u be 5 to the x, then this is u squared plus 7u plus 10 equals 0. Now this is quadratic, so we can solve it however we like. This one happens to factor, so this is u plus 5 times u plus 2, and that means that equals 0. So u is minus 5 or u is minus 2. But now we can switch back to our x's. So remember, u is really 5 to the x. So this says 5 to the x is negative 5, or 5 to the x is negative 2. All right, and now we can solve these two equations. Now these two equations, right, if we try to take log base 5 here to solve these equations, we're going to get this. Log base 5 of 5 to the x is log base 5 of negative 5. And then something similar over here. But log base 5 of negative 5, remember the domain of the logarithms is positive numbers. So there is no logarithm of negative 5. So this doesn't have any solutions. The same thing happens over here. You end up taking a log of negative 2, but there is no logarithm of a negative 2. So there are no solutions there either. So this equation actually has no solutions at all. There's no number x that will make this equation true if you plug it in. One other situation with exponentials that does come up from time to time is this sort of equation where it's kind of a mix of exponentials and, again, I have switched variables halfway through writing the equation. So this is supposed to be a z here. So this sort of thing comes up in applications where it's a mix of exponentials and polynomial type things. So exponential times polynomials, I guess you could say. One nice way to handle this is because this exponential is the same in these two places, we can factor it out. So 2z plus 3 times e to the z equals 0. And this means that either 2z plus 3 equals 0 or e to the z equals 0. But e to the z can never be 0, right? E raised to a power will always be positive, so it can never be 0, so this has no solutions. And then for the other possibility, 2z plus 3 equals 0, we can just solve this the usual way. Z is going to be minus 3/2. All right. So, just because there are exponentials around, don't forget all your other algebra tricks, like factoring things out. Exponentials show up in lots of applications. We'll look at more later, but just to have one now, it turns out that if you deposit $1,000 in an account earning 5% nominal interest annually, and it's compounded monthly, then after X years, this is what the account will have grown to. So how long does it take until the deposit grows to $1,500? Well, if this is the final value of our deposit, we just need to set this equal to 1,500. So 1,500 equals 1,000 times 1 plus 0.05 over 12 to the 12x. But look, this is an exponential equation. So what we should do is isolate the exponential part. So let's divide both sides by 1,000. We get 3/2 equals, and then on the right-hand side, I'm going to do this arithmetic. Let's see. I'm going to get a decimal approximation when I do this arithmetic, but we're going to get a decimal approximation one way or another at the end, so we might as well get it now. Okay, so 1.00416, and it looks like this 6 repeats forever to the 12x. Okay, so this base is so messy that let's just take natural logs on both sides. So natural log of 3/2 equals natural log of 1.00416 repeating to the 12x. Okay, now on the right hand side, let's take this exponent, the 12x, and move it down in front. So we get natural log of 3/2 equals 12x times natural log of 1.00416 repeating. And now we can finish solving for x just by dividing. So x is going to be natural log of 3/2 divided by 12 times natural log of 1.00416 repeating. Okay, and now we can dump this into a calculator to actually figure out how many years we're talking about here. So I'm going to have to be a little careful entering this into my calculator just to get that decimal right. I think what I'll actually do is re-enter, when I come to that point, when I come to entering this number into my calculator, what I'll actually do is just type this out again in my calculator, just so that I get the decimal exactly right. So let's see, natural log 3/2 divided by, and careful about parentheses, 12 times natural log of 1 plus 0.05 over 12. Okay, now I have to be careful to close all my parentheses and then hit equals. Okay, I get 8.126, and this is in years. All right, so it's going to take a little more than 8 years for that money to grow by half.